Can you hear me now?
Yes.
Okay, good. Very good. So one announcement that I would like to make, I just replaced, there was in the homework, as I tried to change my notes from Notability to PDF. There was something weird that happened, and so I redid them on PowerPoint, because usually there are, I don't know, it's very hard to explain, but Notability has different things. You can cover things, you can use different colors and everything. And so it uses different layers to do that. Every time you add something, it's a different layer. And when it translates to PDF, sometimes some of these layers don't make it, or some other times they get mixed up. So in any case, I redid the homework. It's exactly the same, identical. I put it up on same deadlines and everything. So it is on the web. And if you go to your class, and then you will find the homework in 2 different places. Okay, so because some of you are asking. So let me just go back, if I may, reduce this a little bit. Oops. I need to remember where I cannot touch it. Okay, so if I go, let me go home for a moment. This is home. Here you will see on your screens. Does anybody know how to project this on the table screens? That's the one I don't know, but in any case, I'll try to figure it out for next time. So when you go to, and then let me see. How am I gonna do that now? Oh. Okay, 1 second. And here. Okay, that's what I wanted to do. So when you go here, you're gonna see homework set 1. If you click here, it's gonna take you directly to the individual homework. And then it's gonna take some, here. Okay, so you can do it from there, or you can go to your assignments there. And then in assignments, you will see individual homework 1. And then you can click there, and then it's gonna give you that. All right, so there are 2 different places. Also, on home, I'm trying to use this for everything. So there's a lot of information, I understand, but this is where I have the videos, all right, from the previous 2 lectures. So if you click on this, on any of the 2, if you click on this video, it's gonna take you to YouTube. Everybody can hear me, is that right? Okay, so you stop that. So those, okay. That's how it goes. I hope it's gonna be useful, because you don't have to, as long as I know how to get out of here. There's so many things. Okay. So I'm trying to put everything here so you don't have to run into many places. But what I would like you to do is to become familiar with this. It's not so much work. I want you to become familiar, all right? So you know where to find things, okay? All right, any questions about this so far? Okay, so today, we are in week 2. And also here, I show you which chapters, what sections of every chapter we're gonna cover. And this week is a review. All right, so it's not new. We don't introduce. I mean, it's gonna. We are gonna. You have seen things before here, and some other things as well. It's gonna take us a few weeks before we start talking about totally new things that you have not seen them before. But this one, we're not going to be able to cover to spend more time on this because it's fundamental, and we have a limited number of weeks to cover a lot of things. Okay, so here. On your textbook, it does not matter what kind of edition you have. I never pay attention to editions because usually most of the time is fine print. Mostly maybe some of the chapters don't have the same numbering if they introduced something, but usually the existing chapters, and these are fundamental chapters, will be identical. If not identical, 95% the same. Our book, I liked it because it has a lot of examples. So it solves a lot of examples. So look at these examples, all right? And if those examples are not good enough, then you can let me know, and then I will do more solutions. I'll do solutions on here during the lecture, but my advice, look at the example, solve the problem, solve these problems in the book before you do the homework, all right? Okay, so today we are going to start with scalars. That's what I had on the board. And if I can minimize that somehow. Okay. All right, so somebody's going to tell me how, do you guys know how this thing works with that you touch it? I mean, electronically speaking. Not how to do it. Do you know how? This hand? Okay. I have to just tell you that
it's 3 o'clock.
Okay. And other days, maybe from the side. Okay, I just need to figure it out. Okay. Scalars. Why do we have all of these types of different mathematical and concepts or mathematical representations for some natural phenomena? All right, because that's what we are trying to understand. It's not important. The math, of course, is important, but for us, math is the language. All right, so why are we using scalars, vectors, matrices, and tensors? Obviously, you would not, at least at this stage, see things that are not directly connected to a physical situation, phenomenon. Scalar, why? Because we have a lot of variables that we want to measure, which do not have direction, all right? Could you give me some variables that you deal with every day that do not have direction? Yes. Temperature. Anything else? Weight. Anything else?
Speed.
We'll come to this.
Well, I don't mean velocity. I just mean the quantity of speed.
Speed is something that we don't use in physics. Velocity we use, because speed means that you are moving, but it's not informative enough. All right. Yes, you can say I have speed or something, but what does it mean? You're going somewhere, but then it's more of a literally kind of thing. All right, we are using it in speech. We understand what it means. If it is part of a sentence, yes. Yes, that is pretty good for us when we talk in informal, not in accurate way. All right. So when it comes to engineering, we try to be accurate down to as fine as we can, because we'll talk about this, but and standards do that. In fact, if you read some of the standards that the Society IEEE, for example, publishes, it can be 250 pages because everything is defined. Everything is defined. So if you follow these standards, then you are precise in what you say. But in any case, for this one, I will use velocity. But there is another one, humidity. All right, humidity, and so forth. What else? Time, of course. The one that we use the most. Absolutely. Now, so they have units, all right? Units and directions are different things. They have units, they have values, but they don't have direction. So for all of those, we use scalars, scalar functions. And scalar functions, like in function f, can be multivariable, all right? Can be a function of space, can be a function of space and time. So practically, I will remove that. Oh, I put t at the end, yeah. So I have it, but it could be,
Professor,
yes.
we can't see your right screen where you're writing on the sheet. We can only see the Canvas page.
You don't see,
We just see the
oh,
Canvas browser.
you see the Canvas browser. Okay, because, okay, then let me get out of there for a moment and then you tell me. Thank you for telling me, because I stop sharing here. So what do you see here? Do you see, obviously you see everything very small, isn't it?
Yes, ma'am.
Yeah. Okay, let's see. I don't know how else to do that. The other thing I can do is to not write, because when I realize that these things, they don't even show when I write something. So what I may do next time, I will not do it right now, but next time I have my iPad and I will connect my iPad. So I will write there and then you will see it. So not today though, it's gonna take us some time trying to do that. So I will not write there. Let me just get rid of this for a moment. And then I will go back to sharing. And then I will focus on this. Okay. So, and let me expand this for a moment, since we can do that.
I think you could share the big screen if you go to the share screen and then you click your screen on it.
Which screen?
Like if you go to share screen and Zoom, you can choose the different monitor to stream it.
Ah, okay. Well, I'm using this one right now. Can you see that? You can see that, isn't it?
Yeah, I can see.
Okay, perfect. I'm not going to use anything else. There is no need for that for today. But there is going to be a need to do the next time. Start doing some examples. In any case, scalar. Vectors now, so we have scalars can be functions of multivariables, all right? Space, time, and anything else. Vectors. Vectors are for quantities that have direction, all right? It does not, it could be velocity, it could be force, all right? Anything that has, it either has a motion, so it moves from one point to another, or it has the potential to create motion. So a force, for example. That's what it is, usually vectors. This is vectors. In fact, if I wanted to ask you to review something from this, I will say 1 and 2. Properties that involve 1 and 2 are the most critical for our class, okay? And then, of course, we have matrices and tensors. Have you heard what a tensor is? It's a very, you're not going to see it unless you go to graduate school and you do something as a lot of math. But in reality, it has meaning. A tensor is a matrix where the elements of the matrix are vectors. So why can you use a tensor? If I have a system, let's assume that is a gravitational system, and there are multiple forces that apply, all right? And let's assume that there are multiple discrete forces that apply. Now, all of this is it's a simplified description of a more of a complex problem, but simplified. So we discretize the forces. And then if you want to represent that, if you want to represent all of the forces together, all right, and what their impact is if they are in if they apply to specific objects, the best way to do it, if you have a set of multiple vectors and you want to represent them as one set, is to use a matrix form, where then, of course, if it's a combination, if it's a set of forces, and I would like to see, I have a problem I would like to characterize. So I have multiple, let's assume that I have multiple forces here because there are so many bodies and they're moving around and everything. And I want to represent the whole thing as a system, then the forces will be the elements of the matrix, and there will be vectors. And if you represent them, then the matrix, you can call it a tensor, like that. And there is also another similar to vector representation for tensors, but tensors exist also. Why tensors are important? Materials. There are materials that have properties that are that vary with respect both to space and time. And some of these electrical properties, they are not necessarily scalar properties. They can be fields, all right? So fields are vectors. So for example, if you have a material where then the field changes throughout the material, both in direction and in value, then you cannot represent that material without having a tensor in place. All right, so these are very advanced materials that are very complex. You don't necessarily see them in real life unless you may see them in very small quantities when they do interesting properties. I'll tell you of a very interesting material that is very used in research nowadays, and those are called topological materials. What is the interesting thing about topological materials? They look like a matrix. It's like they look like a honeycomb, all right? That is like has spaces, air spaces. They look like that. And then if you design them accordingly, and it can be either from polymer, it can be from other materials, then they change their stresses according to their position. So you can have a material that is very stiff on one surface and is very soft inside the volume. You have materials, this material, you cannot represent it within either a vector or a scalar. You have other materials that, in fact, I was reading today in one of the IEEE magazines that comes that they have identified materials that can store energy on their skin, which is similar to that. I mean, you know how you store energy. You take real energy, electrical energy. It could be an electric current that flows and then translates that energy into mechanical energy. When you hold then the mechanical forces in place, you don't lose them. Then you say that you store energy, because if you know how to translate mechanical back to an electric current, then practically you have a computer, but all of the memory is on the skin. Very interesting materials now. People are going to use them for some amazing things, especially for prosthetics, when you can put something that can make you have a feeling at the end. That's very interesting, you know, for somebody who has lost an arm and they can make it so you can touch something and then you feel it like I do with my real hand. That's going to be amazing, but we're very close to doing that. I mean, the research is in place. Okay, so let's go now to scalar quantities. We talked about the temperature, vector quantities. Vectors, we talked a little bit about that. When you see a bar, a flat bar over the vector, that's a vector. When you see a hat, it's a unit vector. And you remember what how we talked, I don't know whether, does this write over here? Yeah, okay, I'll write a little bit here. A unit vector, if you have a vector like this, all right, if you have this vector, and as a matter of fact, does it make it thicker? No. Vector A, a vector here, which has the same direction like vector A, but a magnitude of 1 is called a unit vector. Okay. And how do you calculate the unit vector? Exactly from here. So for example, if I know this vector A, and if I know its magnitude, if I divide this vector by its magnitude, it gives me the unit vector. All right, so whenever you see X, that's the unit vector along the X direction. Whenever you see Y, is the same thing, all right? Y and Z. So this you will see them in we use them to indicate direction only. Since there is no magnitude, then you only indicate direction from that. All right, let's move then.
Excuse me, ma'am. We can't see when you write on the screen.
That's okay.
Either.
I understand. We'll fix it next time. There is nothing I don't know how to do this right now. I mean, I have limited knowledge of this system. So I will try next time to connect my iPad, and I will write here. I will write up there so you can see it. I did not write anything important. It was an X with a hat. So here what you see are, here we have vectors, and it's important to characterize these two vectors, both in magnitude and direction. In this particular case, this can be a satellite, all right, to a planet. It could be the moon, or it could be Earth to the sun. It's very, of course, idealistic how it goes, but you have this small mass here came into the gravitational field somehow from a far distance with a velocity. But since it was moving like this, then the gravity started growing as that it applied to it. And while at the same time the velocity was forcing it to go along that direction, then gravity was pulling it, and eventually, for this particular case, it stabilized around this circular, okay, motion. So the two forces, we use them there like that. You see the U here is the unit vector for the velocity and has the direction of the velocity, which is perpendicular in this particular case to this mass. Now, I think, and I don't believe I'm wrong, that when you did physics, you solved the problem when the one charge was coming into a magnetic field. Did you do that? That shows that the charge goes like this continuously? Okay. Well, not exactly the same, but something similar, because in this case we have gravity. In that case, we had the magnetic force, all right, that applied. But that's what happens. And then here for gravity, we have R. Usually that's how many people show it, with capital in this particular case. It's along the radius that connects this point to the center of the large mass. And then it's the unit vector, obviously. So that is and then matrices here. As I said, a lot of times I gave an example here. You have a house with 4 rooms, and I would like to measure all of the temperatures in each of the rooms, and then also to see how those vary with respect to the thermostat, which in my house is a big deal. I have to tell you, so I may do that one day if I have time. But so what you do is that you take multiple values here, you take multiple values there, you find the averages. I mean, at the same, over a period when the weather is about the same. And then you create a relationship between these two. And this matrix, it's very interesting that this matrix, why is it important? Because this matrix is independent of the thermostat and of the temperature. The matrix is only characteristic of the geometry of the house. The materials, if you have glass, if the rooms are big, if they are connected, all right, the whole thing. And so interestingly enough, what you're gonna find if you get lots and lots and lots of measurements and you do the same is that this matrix, the values will probably try to converge to something that is independent of the temperature. And that is characteristic of the house. So you have a matrix that is called the transfer function. We're going to use it in, we are using it, and you will see it, not in this class, you're going to see it in 453 or in a class like that where we develop filters and stuff. And then we talk about the transfer function, which is a function characteristic to the system and does not depend on the input. All right. So this matrix, you can consider it as that. And in fact, as you can see, is the temperature versus the reading from the thermostat. If now I were to have a problem like this, it's not showing in real time, but practically here you have the nucleus of an atom, and here you have a particle. And the particle comes with a very high speed and it hits this. And then some of these particles go away on their own, or that may be split depending on how big this one is and how much velocity it has. It may split that into smaller pieces, or it just may have a few, you may keep its shape and have a few of the particles go away. If you consider that as a system, and if the velocity of each one of those, it's one of your parameters that you want to characterize, velocity has a direction. So, and you have multiple particles that go, this also goes, each one of these has the same velocity like the whole mass. And these ones have their own. The moment these hit that, then some of them, those that they leave, they start having their own velocities and so forth. It's a complex problem. And if you want to characterize this problem, you definitely have to incorporate the idea of a matrix. But since the elements of the matrix will be vectors, this matrix automatically becomes a tensor. All right, so that is, so you see, this is not just the crazy idea of somebody who had nothing to do, but we developed them because they were important. Okay, now, these are matrix representations. You will see somehow always matrix representations of a vector and a matrix and a tensor. Yes. The tensor is a matrix where the elements are vectors. If it's a matrix whose elements are velocities or forces, and forces are vectors, then the matrix will be a tensor. Okay, so here you see it. It's 1 times 2 vector. As elements. Yeah. Okay, sometimes you may see it in this form. But in this class, we're going to see vectors like this. Okay, so what now we are going into vector properties. Most of the time in electrostatics, mostly, and in some magnetostatics, but mostly in electrostatics, you're going to get a vector, not like this. I mean, you may get a vector like this, but most of the times I will give you the starting and the ending points. A and B. I will tell you there is a vector AB where A is 0.013 in the Cartesian system and B is a point -678. And then I will tell me first of all, what is the magnitude of this vector? And then I may ask you other things, all right? So it's easier to give a vector by its points as opposed to giving it in a different way. So you need to remember that formula, always. You always, to find this, you always subtract the coordinates of the starting point from the coordinates of the ending point, all right? A, B. So it has a direction from A to B. And when you do that, you subtract like this. So that's going to give you the vector. Then, so now here, you got your two vectors, A and B. A and B. And then the question is, how do we find the sum and the difference? Now, this is what you're going to see in the book, but how did you learn to do it yourselves? Do you remember this or that? Or what do you remember? Because I'll tell you, I don't remember this. I always remember the process of doing this. So to find the sum, you have to create a path with the vectors that goes to the same direction. Like if a vector goes from here to here and the other vector from there to there, I cannot move along this path because I can only go from here, here, there, and I can only go from here, here, on that. So what I do is I move vector A, I do a translation, and I place it so its starting point, which is here in the beginning, here, I translate it and I place the vector like this. Like I place it, so I create a path, I place it right at the end of the B arrow. But it's parallel to its original. That's a translation. And I do it so now, if I start in the beginning of B and I walk, I'm a little guy that I go there, I can go from this origin to the end of B, and then from the end of B on this parallel vector to A until the end of A of that. And then if I connect this point with that point, gives me A plus B. Okay? Now, that's how I remember it. Because sometimes when you remember it like that, can be funny on how the angles may make you make a mistake. All right? Because visually, this picture may change substantially on the basis of what is the angle between the two vectors, whether it's narrow or whether it's wide. All right. Now, if you follow that, and I can only bring the vectors one next to the other in a way that I create a continuous path, all right, then how would I do the difference between the two? The difference, say, I have to take to subtract A from B. So I will move A from here, but then I have to change its direction. So I'm going to flip it. All right, so instead of going from at the end of B in the same direction with the original A, is going to go from the end of B to the opposite direction. So I still have a path I can follow, which is a continuous path. But if I go along this path, I'm getting that. I'm getting the B minus A. That's how I do it all the time without having to memorize pictures. All right, so I want you to remember that. So that is important. We'll see that a lot. The other thing which is very important, the inner product and the cross product. And let's try to understand why these are important. The inner product, you have seen this before, is that right? Okay. Can you tell me more or less what is the inner product? What is it? What kind of information it gives you when you have two vectors? Not really very specific, but the most important information an inner product can give you. When I have, yes. The projection rather. Yeah, so that tells you that when you project one vector on the other, there is some projection that it tells you if I have two vectors like this, and then if the inner product is not zero, practically tells me that when I make a projection of one vector on the other, it's going to be non-zero. How else can we say that? If the inner product of two vectors is zero, what kind of information you have? That the two vectors are what? Perpendicular. If they are parallel, what is going to happen to their inner product? It's going to have its maximum value because they are parallel. So the projection, if you have two vectors which are parallel, the projection of any of these on the other is going to be the full vector. See? And the product of the two is going to be the product of the two, practically of the magnitude of the inner product of the two vectors is going to be equal, if they are parallel, to the product of the magnitudes of the two vectors. That's the maximum value you can get. But when they're perpendicular, then you get zero. So that's an important information, all right? How about this? What does that tell you when I have an A cross B? What happens when A and B are parallel? It's zero. Okay. When they are parallel, it's zero. So you need to have this maximum when they're perpendicular. The opposite of the inner product. The inner product is maximum when they're parallel and zero when they're perpendicular. This one is maximum when they're perpendicular and zero where they're parallel. Yes. This one is a different angle that shows that the vector A cross, so A dot B is a scalar, but A cross B is a vector. And this vector, in addition to having a magnitude that is controlled by this angle, the direction of this vector is always perpendicular to the direction of the plane, or perpendicular to the plane that is defined by the two vectors. All right, from geometry, we know that any two vectors which are not aligning, we are not collinear, meaning on the same line. Any two vectors which are not collinear define a plane, okay? A unique plane, only one. Now, in that one plane, the direction of this is always perpendicular to that plane. And that is important, not right now so much as when we start the vector calculus on Friday, and we are going to introduce divergence and curl, which then have meaning when they apply to forces, all right, or to fields, to other vectors. They have a particular meaning. But here, this is the two. And in fact, today, talking about that, today I have already assigned to you an exercise which does not have limited time. It does not have limit. If it does, if it were to have limited time, it would tell you. It would tell you when you see the exercise. This does not have one. And then I would like, on the basis of these properties, to identify which statements are correct and which statements are not. And there is a number of them. And you have between today and Wednesday to do that. Okay, so just you can, it's not going to be difficult. I just want you to do that, to go through this. Okay. Now this is, we have already talked about the vector. In this particular case, the vector starts at the center of the coordinate system and extends up to point P. And P is, say, it's an observer in this particular, it does not matter, it's a point P. And I gave you this vector like this because, why would I give you the vector like this? Because one point is at 0. And you remember what we did when you have a vector between points A and B, vector A, B. If I give you the 2 points A and B, then you have to take all of the coordinates of the ending point, and from those subtract the coordinates of the starting point to find the coordinates of the vector. But here, because the starting point is at 0, all coordinates are 0 there, so practically this vector has the coordinates of the ending point only. All right? So it's easy. Okay, this vector here, it has a projection, you see? We call point P prime to be the projection of point P on the XY plane. And similarly, you may have projections on the other planes for a vector like that. So we call it like P prime. And that is a vertical, is parallel to Z, obviously. Now, we talked about the unit vector, which is practically this little vector here that only has a direction, but not magnitude is 1. It only indicates the direction of vector A, and we find it from here, obviously. So if you want to find unit vector A, then practically, let's assume that P is 0 in A sub X, 1 in A sub Y, and 1 in A sub Z. All right, so we have Y plus Z. If point P was the point 0, 1, 1, all right, in the coordinate system, then I would have A would have been Y plus Z, all right? And that will be my A vector. And then I will have to divide it by its magnitude. Now, this is the magnitude of the A vector. So how much would be the magnitude of the vector Y hat plus Z hat? Square root of 2. Okay? That is 0. This is 1. 1 to the second 1. 1. And A sub Z is another 1. 1 to the second 1. 1 plus 1 equals 2. So the magnitude of A sub 2 of A vector is the square root of these, and therefore is square root of 2. So if I take the Y plus Z vector and divide these, both of them, by square root of 2, practically I get my unit vector. Not that I need it all the time, but just so you can see how it gets to come out. You will need to know that very carefully because we will need that all the time, all right? We will need this all the time, so you need to know how to find it. Okay, any questions so far? Okay, so here, these are the traditional properties. This is something you need to remember. This is the most important. The one that I have in this rectangular, in the brown rectangular shape. If I have a coordinate, and that's important because when you start doing calculations between vectors, you need to remember these properties, all right? It's the equivalent of multiplication, summation, whatever else we do in scalars. So x dot x is 1. Why is that? Because x by itself, they're collinear. So the inner product of the two vectors is going to have its maximum value. Since x hat has magnitude of 1 and x hat has magnitude of 1, the inner product is 1. The same thing with each one of them. So the inner product of a unit vector with itself is always 1. Okay. they cross, if the unit vector, if the inner product of the unit vector is 1, what happens to the cross product of a unit vector with itself? Why is it 0? Because it's maximum when they're perpendicular, all right? And it's 0 when they are collinear, and X, Y, and Z are collinear with themselves. So this is 0. And the same thing would apply to each one of them. I did not repeat it, but these are important. And I will tell you also why this is important. So X cross Y is Z. And how do you find the direction? You remember the right-hand rule? Okay. A system, a coordinate system, rectangular coordinate system, and every one of the other ones is defined as a positive coordinate system when we follow the following rule. We always move counterclockwise, all right? So if X is this one, Y is this one, I'm trying to reproduce the XY system, and Z is this one, then X cross Y gives Z. Y cross Z is going to give X. Z cross X is going to give Y. Remember that, because what happens if you, by mistake, you put Y first and then X second? Is this going to be true anymore? So if X cross Y equals Z, what is Y cross X? Negative Z. So if you don't remember the order well, you miss a sign. And then to remember that, always use this. Your right hand, for those who are left hand, is a problem. So your right hand, all right, and counterclockwise, always, like this, counter. So X, you don't go like this, you go here, X, Y, Z. X cross Y gives Z. Y cross Z gives X. And Z cross X gives Y. So you will never forget a positively defined system. That is important, because if you don't define it well, then you are losing, you're going to make a mistake because of the signs. So that is critical, okay? Then I'm sure you remember this. Of course, if you are to sum, you sum the parts independently. When you get the inner product, you create that scalar. Fundamental properties. And this one, also, I don't know how you learn how to remember it, but I always remember it like that. Since the first time I remember how to do it. It's not the only way. I'm sure other people remember it differently. They put a plus here, they change that order, but in any case, for me, that's what it is. That's why I wrote it like that. So remember, stay consistent with what you feel comfortable. Don't try to change the way you remember this, but these are important things. Very few things you remember by heart, but these are important conventions, all right? So at least if you see my solutions or something, you have to recognize the reason I'm putting these minuses, because from the beginning of times, that's how I learned it. Okay, other important properties. Of course, commutative relation, all right? So you can change the order in the inner product all the time. It does not matter how many vectors you have in a product, you can change their order. But when you start, and then of course distributive, all right, here. And of course this one. So this is important for the inner product, okay? The second set that I have here in purple are for cross products. There you have to be careful. You always remember that with cross products, be aware of the sign. When you do anything with cross products, remember that it is possible, if you're not careful, to make an error with a sign. So remember that there is no commutative relationship. There is a negative sign here, obviously. So what is the interesting thing? Remember that, because I have a question in the quiz that's going to be related to those. All right, so just a little bit is the same relationship in a little bit different form. Okay, now it is distributive, however, and this one gives 0. All right, A cross A is always 0 because A is collinear and identical to itself. So obviously it's going to give 0. And here, this is a little bit, I don't remember them. I have to tell you, from this point on, I always go back to the book. I don't remember things by heart very easily. So it's not a crime to not remember those here. Since I don't remember them, I cannot remember them, then I don't expect you to remember them, but know where to find them, all right? In the books, usually those relationships are on the front cover, somewhere, put a note in there so you can go quickly. But these are the relationships that in fact they can get complex, and I don't plan to give you any crazy formulas to go back and forth because we are not gonna go that far. But it's important if it happens that you have to use them in a solution of the problem to just be aware so you don't. If you are aware that it's easy to make a mistake, then you're gonna know that you have to be careful, all right? So you don't just do it casually. Okay, so these are the properties. These are all the vector properties. You've seen them before. We remember them now. You're going to have an opportunity to revisit them. And I have to tell you that whenever we will solve problems, starting different problems, I mean, electrical and magnetic field type of problems, I will remind you of the properties. All right, and we will always remember them. Any questions so far? Okay. Next time we are going to do, so we'll do on the basis of everything, you can do your exercise. Don't need to know anything more than what we have already covered today for the exercise. All right, so take your time to do something. I would probably do it not tonight, but tomorrow to just go and remember. Next time, we are going to get a little more complex because we are going to talk about coordinate systems. And while in the Cartesian coordinate system, things are easy, you go to cylindrical or from Cartesian to cylindrical to spherical, and then things can get kind of complex. But there are formulas in the book for translation. I have put already one formula for your, I have put them on one matrix. We are going to do this on Wednesday. Okay. Any questions before we end? Questions? Okay. Good, good. So we are doing our review this week, and then things will get a little more interesting when we talk about the real problems. All right. Thank you.